All right, here we go. Do you guys know that where we live up here in Indiana, which would be probably somewhere right around there, did you guys know that we are not too far from a fault zone?
Nope.
It's not going. Wake up! Oh, I gotta push play or start, probably.
So we don't talk in this.
Okay. Did you guys know that where we live in Indiana, we're not too far from a fault zone?
No, we do.
Seriously, did you guys know that?
No.
Have you guys? How many of you have ever felt an earthquake? No one has ever felt an earthquake? Really? Wow. You guys need to get out more.
Well, I'm sorry.
I felt two in my life. Now they've been real minor. You know, just kind of like just a little wiggle kind of a thing. Yeah, nothing major. I mean, I wasn't in any falling down buildings or anything like that. Both of them were like real early in the morning, and I was still in bed, trying to sleep. It was enough to wake me up, but it wasn't real major. Right down here is the New Madrid seismic zone. There's a minor fault line right down there. Okay, we've got an even smaller one up here in the southwestern corner of Indiana called the Wabash Valley. Wabash, right? The Wabash River comes right down this side of Indiana. Did anybody know that? The Wabash River. Okay. 1860 or 1861, I can't remember for sure. There was a strong enough earthquake there in the town of New Madrid, Missouri, that it actually caused the river to flow backwards for a short period of time. Destroyed a lot of the town. Okay. When I was in college, which would have been my freshman year of college, would have been the fall of 1990. Okay, yes, I was alive in the 1900s. I know I don't look it, do I? See, good answer. The fall of 1990, I was at a college just south of Indianapolis, and there was a famous geology professor. I couldn't tell you what his name is. He was so famous. He was predicting that fault line, the New Madrid seismic zone, was due for another big one. And so I remember as a freshman in college, we were practicing earthquake evacuation drills from our dorm. Nowadays, what do we do when we have an earthquake drill here? Duck and cover, right? Or duck, cover, and pray,
Yeah.
right? But we didn't do that. We were running for the door. Okay, I don't remember if there was a siren or what there was, but we were running for the door. And kind of the running joke was to see how many boys were running out of the girls' dorms because boys weren't supposed to be in there. But that's a whole different story.
Tell us.
But that's all there is to tell. I don't know. It wasn't me. I wasn't there. Sure. Who said that? Who said that? Somebody's going to get themselves in trouble. Okay, here we go. Forces in Earth's Crust, Lesson 1. You read a little bit about My Planet Diary on page 102 about India getting together with Asia, right?
Yes.
Pangea, a long time ago, India was way down here, and the convection forces inside Earth moved India, and it crashed into Asia. Two continental plates colliding, we end up with crumpling or bulldozing or whatever you want to call it. And we end up with Himalayan mountains, right? That force that's driving India up into China is still going, so the mountains are still getting created taller and taller and taller. So what does that mean is happening to the size of the subcontinent of India?
Getting smaller?
It's getting smaller. I don't know about you, but I'm a little bit worried about what are we going to do with those 2 billion people when India keeps on shrinking? Where are they going to go?
Like, not here.
I don't know. Thankfully, it's only moving a centimeter or two per year, and so we don't have to plan for it today. We got time to figure it out. Okay, so here we go. Forces inside Earth's crust. Is it better for you to just have a minute to write before I blab?
Yes.
Okay, we tried to talk about that before, but so let me give you a moment to jot down, and then I'll talk. Because I did give you another set of notes that has a lot of writing, didn't I? I sure hope that thing is recording my voice. Okay, it's probably good enough to record that then. Jacob, got a question?
No.
Okay. Filling in your notes?
Yep.
Got it all done already? Can you read it?
Yeah.
We're going to talk about three types of faults today: normal faults, reverse faults, and strike-slip faults. And what you're going to notice is that all three of these types of faults are going to be directly related to the three types of boundaries that we talked about in our last unit. What were the three types of boundaries we talked about in our last unit? Alex?
Divergent, convergent, and transform.
Okay? They're going to connect to these. Okay, we're connecting dots here. Okay? So when we're looking at any situation where there's a fault, okay, and a fault is where there's movement along that plate boundary, the type of fault that we have is going to be determined by the type of stress force that is being applied to the rocks. Okay? So if it's the three stress forces we're talking about are tension, pulling them apart, compression, pushing together, and shearing going side by side. Okay? So we're going to get into each of those three faults. We're going to talk about examples of them. We're going to talk about the stress forces that cause them. And we're going to talk about what are the results of that movement. What do we get at the end? So let me give you a few seconds here to jot that down about normal faults. First thing I want to do is play a little game. You can play along if you'd like. On your desk, find, and if you don't want to, if you just want to watch me do it, that's fine. Find two items. Could be two books. Could be a book and a pencil box. Could be a book and a calculator. Could be a folder and an iPad, whatever. Okay? So find two objects that kind of have flat surfaces. Okay? Take one and put it on top of the other. Okay? You don't have to play if you don't want to, but you can play along if you'd like. Okay? Which one is under the other? This is under the other, right? This is the under one, the one that's under. Okay? Now what happens if I take this and I angle it just slightly? Is it still under?
Yeah.
Okay? Still under? Still under? Still under? Still under?
Yes. No. No.
Still.
No.
Okay. The key is you got to be able to identify what's on the bottom. Okay. It may not be totally on the bottom. What if I do it this way? Now which one's on the bottom?
The small one.
Same one. This one. Okay. This one's still on the bottom. You see the angle between the two where the surfaces meet? Which one's on the bottom of that angle? This one, right? Okay. Same thing here with these faults. Okay. Hanging wall and foot wall. The hanging wall, even though this picture is kind of tilted, this side of the line, okay, the left side of the line is on the bottom of the angle. Whichever one is on the bottom of the angle is the foot wall. All right? The one that's on the top of the angle is the hanging wall. Follow me? Okay? So when we're dealing with these big, large blocks of rock, okay, now these big blocks of rock, they could extend miles and miles and miles, hundreds or thousands of square miles, okay? For a normal fault, we've got these two blocks of rock, and where they meet is called the fault line. Which one is the hanging wall, the right or the left?
Right.
The hanging wall is the one on top of the angle, right?
The white one.
So it's the one on your right. Okay, the foot wall is over here, the one on the left. Am I on that picture at all?
A little bit. No. Yeah.
Is that better? Okay.
Wait, how's the white one?
So now, how's the right one, the hanging wall? It's on the top of the angle. You see this? See the slope here? Okay. Which one is more on top? The one on the right. Okay. So it's the hanging wall. The one that's more on the bottom of the slope is the foot wall. Okay. You need to be the director of the show. So if I need to.
Yeah.
Tension is what is acting. Okay. Tension is our stress force at a normal fault. So tension means pulling apart. Okay, now these are giant, huge blocks of rock. Okay, we're not just simply going to pull them apart. That doesn't happen because they're too big and gravity's too strong. All right, so because it's on a slope, when tension pulls them apart, the hanging wall simply slips down the slope. Okay, the hanging wall moves down the slope because tension pulls them apart. We don't have this pulling apart and then we got this big gap in the middle. It doesn't do that. The other thing that we don't have, that this model doesn't show, is that the surfaces where these two things meet aren't perfectly flat and smooth. Okay? You got to picture a bunch of rocks jutting out on this side and a bunch of rocks jutting out on this side. So that when they meet, okay, gravity wants to pull this one down, but the rocks they're kind of sticking out on each side and they get stuck on each other. Is that making any sense? Okay. How long do they stay stuck on each other? As these things keep pulling apart, gravity wants to keep pulling this hanging wall down and down and down. When does it actually move? When the rocks can't handle the stress anymore. When you put so much weight on those rocks that are locked together that the rocks break. And then all of a sudden it does the magic thing like this. It goes, it's going to have a big slip. How far does it fall? It's going to fall however far until the rocks get hooked on each other again from each side. Does that make sense? Okay. Rocks can handle stress. Just like your pencil can handle stress. Okay, let me get something over here. Just like this meter stick. Okay, meter stick made of wood, just like your pencil, right? It can handle stress. Okay, how much stress can it handle?
A lot.
We could find out, couldn't we?
Yeah.
If I kept applying stress, Logan might know. How would you know? Huh. Okay. So for a normal fault, look at the description. The rock above the fault, which is the hanging wall, is going to move downwards. It's going to slip down over the rock below the fault, which is the foot wall. So for a normal fault, tension pulls them apart. The hanging wall moves down. And it gives the appearance that the foot wall is up. Now in this picture, we got a couple rivers or streams, right? Which way are the rivers flowing? Can you tell?
Right.
Are they flowing to the left or are they flowing to the right?
Left. Wait. Left.
You got to have a reason. Carrie,
Right, because.
you think they're flowing this way?
Yeah,
Why?
because it's kind of going on a tilt like this.
Is there a river up here though?
No. There's one to the left.
Wouldn't there be a river up here if they were flowing to the right?
Yes.
Yeah.
I don't know. I think they have to be flowing to the left, personally. But what else might you see if they're flowing to the left? Wouldn't you see it kind of pooling up right here? Probably. Okay. Reverse faults. Write this one down. Everything about a reverse fault is essentially the opposite as a normal fault. For a reverse fault, the two red arrows on the outside, now we have compression pushing them together instead of tension pulling them apart. All right? So if we have a hanging wall and a foot wall, okay, remember the hanging wall is under this angle. You see the slope right here? Okay, so this is the foot wall, this is the hanging wall. Let me put it just like they got it. Yeah, okay. Now if I take my hands on the outside of this thing and I push them together, the one that's on top of the slope isn't going to slide up the slope. Right? It's good. So if I put my hands on the outside, okay, and I'm compressing them, I'm pushing together, it slides up the slope. So the hanging wall now goes in the other direction. Okay? Compression is causing it to slide up the slope. So reverse faults and normal faults are opposite. All right? They're opposite. Questions on those? Last one. It's called a strike slip fault. strike slip faults are best viewed from above. For example, when we did the reverse fault and the normal fault, we looked at it from the side, but I'm going to tilt these blocks so you can see them from above. Okay, now this looks probably like a stream or a river, right? The white thing. It could be a road. It could be a fence line. It could be what else could it be? A river.
Do a path.
Maybe a line of utility power lines,
Yeah.
something like that. Okay. Okay. Now remember, the rocks on either of these surfaces that are connected are jutting out, so they're not going to just slide real easy. Because if they just slid real easy, would it give off much vibration when it moved?
No.
Probably not. So that means earthquakes wouldn't be real strong. It wouldn't be such a big threat. Okay, but it's got those rocks jutting out on each side. Okay, and if this one on my right with your left, okay, if it wants to move this way, and the one on the other side is going to move the other way, the rocks are going to hold it up. They're going to get caught on each other. But eventually, the rocks can't handle the stress. Okay, what stress is it? It's shearing. Okay, and it slips. How much can it slip?
Oh.
Maybe a few feet, a few inches. There's in some cases, earthquakes like this or plate movement like this have caused movement like 10, 20 feet. Okay? That's a big jolt. And that's a real big jolt. That's a knock a whole city down kind of jolt. Okay, that's a big one. Okay, this is kind of what goes on in California. Okay, notice for this one, we didn't talk about which one is the footwall and which one is the hanging wall, did we?
It doesn't matter.
Exactly, it doesn't matter. Okay? It doesn't matter. Because it's not moving up or down, it's moving sideways. It's moving horizontally. Okay? California's got earthquakes like this. That's the kind of movement that goes on out there. Okay? I go back. What kind of plate boundary would this be? Tension, pulling apart. Divergent. What about this one? This would be convergent boundary, and this would be transform boundary. And take a look at this one.
Oh, what the?
Which of the three faults would this one be? Transform. And you can tell because it moved sideways, right? It didn't go up or down. It moved sideways. Okay? This obviously is a very old track and is not used anymore. Okay, let's glance real quick at a few figures that you were asked to do. Page 103, figure 1, you were supposed to draw some arrows here. Okay, for the stress force of tension, the arrows are pulling the plates apart. What about for compression? How did you draw the arrows on this one?
Coming together.
Coming together. You probably had this arrow pointing this way and this arrow pointing that way. Coming together, compressing. What about shearing? Yeah, maybe one going that way and the other going this way. Something like that. Okay. Have you ever heard a pair of scissors called shears?
Yeah.
Okay. Well, think about what shears do on a pair of scissors. The blades move sideways past each other, don't they? Okay. Shearing. Figure 2 on page 104, we're identifying hanging wall and footwall, etc., down at the bottom of the page. For the normal fault on the left, which is this the hanging wall or the footwall right here? That's the footwall. What makes it the footwall, Matthias? You're right. Yeah, it's under the fault. It's under the line. So it's the footwall. And that means that the one on top of the fault or above the line is going to be the hanging wall. So those should be labeled footwall and hanging wall. What about the reverse fault? Same thing, right? This one is below the fault. This one is above the fault. So this is the footwall. This is the hanging wall. We're going to skip that applied on 105 for right now. We may get back to it. Let's talk about mountain building. And here's what I want to tell you about mountain building. Some of the stuff that we're going to get into here on the next several slides about mountain building is not in your book. Some of it is, but some of it is not. Just note that. Let me give you a few seconds here, and then we'll talk about mountain building. You probably thought once upon a time that a mountain was a mountain, right? All mountains are the same. Alex,
Can I take a picture of the text on the bottom of the slide?
can you take a picture of the text at the bottom of the slide? Is there not a spot to write that? Yeah, that's fine. I think that'll be pretty easy though. But you can take a picture if you want. 4 types of mountains we're going to talk about. We're going to talk about fault block mountains, folded mountains, upwarped mountains, and volcanic mountains. Volcanic mountains are probably the easiest, okay? We just call them volcanoes, really, okay? You can tell roughly how old a mountain or mountain range is by looking at what we call its ruggedness, okay? How rugged it is. When we look at ruggedness of a mountain, we're looking at how rough it is, how jagged it is. Maybe it's pointier. Is that a word? More pointy.
Yeah.
Okay. Why would a younger mountain be more jagged and more rugged and more rough and more pointy? Lauren? Yeah. If it's younger, it hasn't been around as long, which means it hasn't been exposed to weathering and erosion as much. So all those rough parts, all the roughness and the pointiness hasn't been worn down yet. Okay, we're going to look at a few examples here as we go. So let's start with fault block mountains. The third word is tension. So what kind of a fault are we talking about here? If it's tension. Matthias? It's a normal fault. Okay? A couple different things that can be happening here with a fault block mountain. Okay? Tension pulling apart. So the hanging wall is going to slip down. Okay? In this arrangement here, the hanging wall is on your right. So as tension pulls them apart, the hanging wall slides down. We get this big block right here that sticks up, right? Our fault block, okay? Our fault block mountain. You could also look at it in another way as tension pulls them apart, these big giant sections kind of tip over or tilt over. Okay? And you create these peaks and valleys that are fault block mountains. Okay? Anybody know where the Sierra Nevada mountains are? No. California, I believe. Okay, the Tetons are up in the northwest, Oregon, Washington kind of area, I think. I'd have to look that up for sure. Here's another example on the fault block mountains. Take a look at this. If you're looking at this in your book, we had to label this. The block in the middle, is it above or below the fault lines on the outside? Is it above or below?
Below.
It's below the angle, isn't it? So this one in the middle is the football. Look at this picture. The one in the middle here, is it above or below the fault lines?
Above.
So this one, we have the hanging wall in the middle. You see the difference? Okay. The one on the out, this one up here, this fault block mountain, let's look at that one first. If this is how things start, let me find, let me get all my props ratings here. Okay, here we are. We got our footwall in the middle, right? As these get on the outside, this hanging wall and this hanging wall get pulled away, it's eventually going to look like this, right? Fault block mountain right here. Well, what if the normal fault is flipped around? Let me see if I can flip these over here. What if now the hanging wall is in the middle? Tension pulls them apart. What did you draw down here in part B?
Middle?
When these things get pulled apart, am I on the screen there?
Yeah.
Okay. When I pull these outside two parts away, these footwalls away, what's the hanging wall in the middle going to do? It's going to slip downwards, right? Did you draw that
Yes.
on part B? If you did not draw that on part B, draw that on part B. In this case, we have two normal faults here. Two of them being pulled apart. Okay? Look at that picture on the bottom right-hand side. Does that look, those mountains look old or young? These ones over here.
That's old.
What gives you clues about their age?
Pointy.
Carrie?
They're like jagged.
Yeah, they look pretty jagged. Now, they don't look very tall, but I reckon, you know, when you think about these being trees, they're pretty tall. Okay, so Carrie, would you say young or old? Yeah, relatively young. Okay, they're still pretty sharp. They're still pretty jagged. They've been worn down a whole bunch. Folded mountains. Compression. So what kind of fault we got going on here with compression?
Reverse fault.
It's a reverse fault, okay? So now, instead of pulling things apart, we're pushing together. I'm gonna use these foam pieces here, okay? If compression pushes them together, it's kind of like if you were to take two ends of if you got a towel or a rug on the floor and you take both ends together and you push them together, what does a rug do? It's gonna wrinkle, right? It's gonna make those folds upwards and downwards, okay? It's folding, okay? Kind of the same thing here. If I push these two together, it's gonna fold, okay? I have these upward bends on this side. Looks kind of like an arch, right? And down over here is kind of a trough or a bowl shape, right? Folded mountains. You ever heard of the Appalachian Mountains? Okay. Anybody ever been to the Appalachian Mountains? You ever been to the Smoky Mountains? You've been to the Appalachian Mountains. The Smokies are kind of a little extension of the Appalachian Mountains down in Tennessee. These upward folds are called anticlines. Did you label this anticline?
Yeah.
Okay. Here's how I remember which is which, because sometimes it's easy to get synclines and anticlines mixed up. The upward bends are kind of like arches, right? The word arch starts with an A. The word anticline starts with an A. So the anticlines are the arches. Okay? The downward bends are the synclines. Starts with an S. It's a bowl shaped or trough, or the word I like to use, a sink. Sink starts with an S. Syncline starts with an S. I know, genius, right? If you're looking at figure 4, you should have had that arrow pointing this way and this arrow pointing that way, kind of compressing together. We got the ups and the downs with the folding here. Everyone okay? You guys have no sense of humor today. Are you guys like wiped out? You get one day without a delay and look at you. You're a bunch of crabby, sleep deprived
Wait, what'd you say?
people.
I looked at the headache.
Yeah.
That's all right. We still love you. Okay, take a look at a couple of these examples. Okay? See that upward bend? Is this an anticline or a syncline? It's an anticline. Okay? Here is an anticline coming up, and then a syncline right here, right? What happened to the top of this one? Where'd it go?
A bird. A bird.
No. No birds. Yeah, got worn away by the forces of nature, right? We got it weathered and eroded. You guys remember back when we talked about ages of rocks, and we talked about sometimes layers of rock just get wiped out and they're gone, and then if new layers form on top of that, do you remember this word that we use called unconformity? Where not always the youngest rocks are at the top, or the oldest rocks are at the bottom? Yeah. The law of superposition. Okay. Take a look at this one. Look at these big folds right here. The rest of it is just gone. It's been eroded away. Okay. This is a photograph of a portion of the Appalachian Mountains. Would you say the Appalachian Mountains are old or young?
Old.
How can you tell they're old?
They're round.
Yes. They're pretty rounded, aren't they? I mean, not that it would be a piece of cake to climb or anything, but compared to what we looked at on that other slide, they're pretty weathered and worn down, aren't they? Matter of fact, the Appalachian Mountains are some of the, if you were to examine the age of the rocks, the Appalachian Mountains are some of the oldest mountains in the world. Alex?
How old does it have to, does the mountain have to be considered old?
I don't know. How old does a person have to be considered old?
10. 10.
70.
I would say that's a relative term. It's kind of what you think.
10. That's 57.
I don't know. Upwarped mountains. We're getting close to getting this wrapped up here. Upwarped. Got two little sections of your notes yet to do. upwarped. You all know what the word warp means, right? If a piece of wood gets warped, what does that mean? Matthias? It may bend.
There's fungi on it?
What's that?
There's fungi on it?
Maybe. Could get weaker. In other words, it's going to be changed somehow. Okay? Now normally we think of if a door or a window gets warped, we think of it not changing in a good way, okay, or a useful way. But it gets changed. So if something gets warped, it gets changed. If we call these upwarped mountains, that means they're being changed in an upward direction. Okay, so the layers or the material, the rocks that are making them are being changed in an upward fashion. Kind of like, let's see if I can do this here. Let me take that out of there, put this here. Say we got something like this. Is that on the screen at all, Esther?
Barely. No. Just the top.
Just the top? Okay. So let's say we got something like this, okay? Here's our arrangement. Okay. What kind of rock is probably on top with this yellow foam? What category of rock?
Lime.
There's 3 categories.
Sedimentary.
Probably sedimentary. Okay, probably sedimentary. If rocks are going to be upwarped in an upward fashion, what could cause a bunch of rocks to get pushed up? What could do that?
Oh.
What about if under this middle block we've got a large body of magma right down here? What does magma want to do?
Expand.
Yeah, it wants to get out. And the way it gets out is by going up. Right? So if we're talking about upwarping, okay, it wants to rise because you guys know the magma is less dense because it's hot. So it wants to rise. It wants to push upwards. Okay? I don't have enough hands to do this. So this middle block gets upwarped. It gets pushed upwards. And I got to cheat a little bit. Got to use more props. I'm going to put this thing right here. So now this has been upwarped. Okay? Let's say we've still got these sedimentary layers on top. Obviously, we wouldn't really have a gap in there. That would be real stuff, right? What's going to happen to the stuff on top? It's going to get weathered and eroded, right? So take a look at the picture that we've got right over here. This block in the middle has been upwarped. Is this nothing blocking this?
No.
No. Yeah. Now is it?
No.
Is it still blocking? You can see this picture?
Yeah,
Okay,
you can
sorry.
see it.
Okay. So this block has been upwarped. Probably some magma or something down under here that's pushed it upwards. Okay? Sedimentary layers right here, look. They're gone up here, aren't they? They've been weathered and eroded away. Okay, these are upwarped mountains. We could also get something like a lava plateau. Okay, we get a bunch of stuff pushing upwards. Okay, you guys know what a plateau is, right? You guys seen pictures of plateaus? Maybe in the southwestern part of the United States, they call them a mesa. You ever heard of a mesa? That's Mexican word for table, by the way. There's your Spanish lesson for today. Mesa. Oh well, it'll stay right there. We'll get it later. Anybody know where the Black Hills are? This is part of the Black Hills. I was there this summer. South Dakota. You gotta go. Put that on your list. Okay. Have you ever been to Mount Rushmore? You've been to Black Hills then?
No.
Oh yeah, it's right in the middle of it. Okay. What about up there in the upper right? Those are the Adirondacks. Anybody know where the Adirondacks are?
California.
Nope.
Wait, I got it, Nevada. Washington.
New York, you're right. Good job. The Adirondacks are in New York. You don't think about mountains in the state of New York, do you? Okay. Now, I need that little phone. Now, I want you to take a look at this one. If the sedimentary layers on top get eroded away, what kind of rock's going to be left behind? Why? Because that's the stuff that pushed it up to begin with, right? So imagine we got a sedimentary layer over the top of this big hunk of white rock right here. It used to be flat. It got upwarped, and then the sedimentary layers, which are easily erodible, got eroded away, and it left this big hunk of magma just sitting right there. Except it's not magma anymore, right? It cooled down to form solid rock. Okay. These are probably the easiest ones. Can you guys see a mountain in that picture?
Yeah.
It's kind of faint. It kind of goes like right in here. Okay, it's kind of hard to see. I'm not sure where I've got that picture off online somewhere. I probably need to update that. Can you tell what continent that picture is from?
Africa.
How can you tell?
There's no way. You can see the trees.
Probably by the trees. That's the clue I would use.
There's no water.
There's no water? Well, maybe there's water right here. Well, at least you're using your clues, right?
Why not this is Savannah?
Volcanoes. Okay, that's really what this is. They're just volcanoes. Okay, remember when we talked about the Great Rift Valley of Africa, where Africa's being pulled apart and the crust gets real thin and we got this magma that squeezes out? Okay, this is Mount Kilimanjaro. This is an extinct volcano. It hasn't erupted for a long time and probably never going to erupt again. It's not even sleeping. It's dead. Okay? But magma came out. It's in that Great Rift Valley where that crust is real thin, so the magma had an easy way to come out. It accumulated over time and made this volcano. Mount St. Helens is a volcano, right? It's a volcanic mountain. They're all over the place. There was one about 2 weeks ago on the island of Tonga that erupted. Have you ever see that one on the news? Okay, when we get to volcanoes, we're gonna look at that one. We'll watch some of that video. One of the tallest volcanoes in the world is Kilauea in Hawaii. Now it's not near as tall as some other mountains, at least not the part that sticks above the water, but most people forget that where is the bottom of Kilauea? It's on the ocean floor, isn't it? Okay. So we always talk about Mount Everest being the tallest mountain, but technically Mount Everest is the tallest mountain on land. That's your interesting fact for the day. Okay. There's Mount St. Helens. This was after it erupted in 1980. Two things I want you to notice. Number one, notice how this side of the bowl is gone. When Mount St. Helens erupted in 1980, It didn't go up, it went out. And this whole side of the mountain basically fell off. Okay? When the eruption was over, the Mount St. Helens was about 1,000 feet shorter than it was before it erupted. This lake right here is called Spirit Lake. It actually used to go behind and go in between these two. But all of this got filled in because the mountain just, it was a giant landslide, just kind of filled it in. Second thing I want you to notice, you see a new lava dome growing in there? What does that mean?
It could erupt again.
Yeah, she's not done. Okay, she's not done. What about this one? This one is up near Iceland. This one's in the ocean. Okay, just a little bit of it is sticking out of the water.
Waterproof.
So it's creating land right here, right? Creating new land. Creating an island. This one is sitting right on the mid-ocean ridge where that magma is coming right out of the mantle. Okay. That's good enough for today. Okay. That was fun, wasn't it?
How long is it?
I don't know. Really long. 51 minutes. Oh my.